Okay, well, welcome everyone to MSU Soil Fertility webinar series. And this is week 2 of Clayne Jones is going to be covering nitrogen fundamentals. And Clayne is MSU's Extension Soil Fertility Specialist. And my name is Jennifer Solf. I'm the Extension Agent for Musselshell and Golden Valley counties. So before we really have Clayne start on this week's topic, I just wanted to cover some troubleshooting tips to help you properly listen as well as view Clayne's presentation and knowing how to ask questions. So if you're having any trouble hearing us, just be sure to check that your volume is up on your computer or whatever device that you might be watching or listening on. But if you still cannot hear us, try just calling in for audio by dialing this number that you should see on the screen, this toll-free number 1-855-797-9485. And then that phone passcode is 120-817-8452. And as most of us know, internet across Montana can be tricky and slow at times, and especially this evening where we're experiencing these awful winds, it could just cut out. So try to, while we're trying to improve reception, please just shut down all other programs that you may have running on your computer and turn your video option off. So by turning that video option off, that's also going to help gain faster reception. And now you should be seeing the screen view during this webinar. Along the right-hand side, you'll see a participant section and a chat panel. The chat panel will be where you can type and submit questions, and I will be monitoring the chat panel and checking that Clayne has addressed those questions. When entering any questions and or comments, you can select who sees what you write, either to everyone, or you can specify to individuals. And everyone has automatically been muted to avoid any sort of background noise. And once again, there is a video icon to turn off your video so everyone cannot see you. And it's also, like I said, improve our internet speed. So with that, I'm happy to hand it over to Clayne.
Great, thank you. Thank you so much, Jennifer. Thank you, everybody, for making it here this evening. Very windy day. I saw in the news today that it blew 125 miles per hour on the top of Mount Sentinel outside of Missoula. And as Montana know, that's usually not our windiest spot in Montana. So it might have been higher than that somewhere else. A really windy day, even here in southwest Montana. So this is week 2 of our winter soil fertility series. Last week was on basic soil fertility and how to read a soil test. I am presently transcribing that. So for those of you who missed it, I hopefully will have that up by the end of the week on our webpage, and it will provide a link to YouTube. And this one should be ready in the next week or two as well. If you do have questions, as Jennifer mentioned, please enter those questions in the chat. If you have questions after the talk, please feel free to give me a phone call at the number shown at the bottom of your screen, or send me an email address. Send me an email at that address. So my goal today on discussing nitrogen fundamentals is to present nitrogen management practices that increase nitrogen fertilizer use efficiency, decrease losses, and increase profits for producers in the audience. As I think probably all of you know, nitrogen is the most common lacking nutrient and also one of our greatest input costs. So one thing I like to think about is, well, where does the nitrogen go? Well, nitrogen is removed by harvest That's not necessarily a bad thing. It's also removed by leaching or runoff. It's estimated that there's up to $1 billion of leached nitrogen in Montana groundwater. We'd much rather have that in our soil or in our crops. My colleague Rick Engel has determined that volatilization, meaning the escape of ammonia gas to the atmosphere, averages somewhere around 18% in Montana, but he's measured losses as high as 44%. So I want to show you how to make sure your losses aren't that high. Denitrification to nitrogen gas means nitrate getting converted to nitrogen gas. We think that's somewhere on the order of 5 to 10 pounds of nitrogen per acre per year. So not as big as volatilization, but it can be, fairly detrimental to yield and to protein. So nitrogen management practices, the goal would be to have nitrogen available when needed and also to reduce losses. How do we do that? One way is through soil testing. You can't know how much nitrogen to add to your garden or your field if you don't know how much is there. Nitrogen rate, I'll cover in more detail next week when we really focus in on 3 major crops in Montana: wheat, canola, and pulse crops. And then we'll also be covering management of nutrients and forages in a few weeks. So nitrogen source, timing, and placement also will help reduce losses and maximize yield. And then also I like to think of the right rotations to supply and catch and release nitrogen from previous legume crops. Conservation tillage often has been found to reduce nitrogen losses as well. Well-timed irrigation, I think, is really important also at reducing losses. And then using, what the 21st century has to offer, a lot of technology. So there's online nitrogen calculators and chlorophyll meters, relatively low tech. There's nutrient tracking tools. There's precision imagery that can help you variably apply nitrogen so that you don't have as many losses. So what does the nitrogen cycle look like? The nitrogen cycle we can think of as, say, starting with organic material. Organic material like organic matter or manure can get mineralized, and what mineralization means is it's just converted over to a form that plants can use. This ammonium can then be nitrified, converted over to nitrate. Nitrate and ammonium can both be taken up by plants. Nitrogen fixation is that process that occurs on legume roots where nitrogen gas in the soil is converted to a form that plants can use it. So here I'm going to focus on losses because, again, except for harvest, we prefer to reduce these losses. Keep the nitrogen out of the air, keep the nitrogen out of the groundwater, put it into your plants, and keep it in your soil. So volatilization, again, is the loss of ammonia to the atmosphere. Leaching is the loss of nitrate below the root zone, often, unfortunately, to our drinking water. And nitrogen can also leave fields in the form of runoff. Finally, that process of denitrification, again, is where nitrate gets converted over to nitrogen gas. So starting with volatilization, again, I think this is likely our largest loss of nitrogen in Montana. Leaching is probably a close second. High-risk conditions for urea and UAN volatilization. So UAN stands for urea ammonium nitrate. We often call it 28 solution because it's 28% nitrogen. When we apply urea to a moist soil or heavy dew, it starts the process of urea getting converted to ammonia. That can increase volatilization. The longer the time is between application and incorporation by either a rain event or snow event or tillage, that will increase volatilization. High pH soils, high soil temperature, crop residue or a perennial thatch or sod, what does that have to do with volatilization? Well, if urea or liquid urea ammonium nitrate gets held up in residue and doesn't get pushed down into the soil, it has a much better chance of volatilizing. Soils that are sandy, why is that? Well, if ammonium can't stick to the soil because it's too coarse, it's going to have a better chance of going out into the solution and then escaping as ammonia gas. Poorly buffered soils, soils that have low soil organic matter or coarse, can raise the pH very quickly when a urea prill hits them. Higher pH again favors volatilization. And then a question would be, a thought question, does application on frozen soil belong on this list? Well, you might think, well, if high soil temperature helps volatilization, maybe low soil temperature decreases. Well, it turns out frozen soil is not good either, and that's because the urea doesn't have a chance to make it down into the soil. It just sits on the surface and slowly volatilizes to the atmosphere. What are the most important factors affecting urea volatilization? We think the first would be surface soil moisture at time of fertilization. If the soil surface is moist, volatilization starts right away. The best case is probably having a half-inch precipitation event or some tillage within 7 days, and within 1 or 2 days would be even better. The worst case is a moist soil surface with only sprinkles for the next few weeks. Those sprinkles aren't enough to move urea into the ground, but they're enough to create this process where urea gets converted over to ammonium and then to ammonia. So another thought question. This was an experiment where urea was applied to a few inches of snow. Historically, we would think that's fine. Snow is cold. It's not going to volatilize. So think about in a 100-pound nitrogen per acre application, about how many pounds of nitrogen you think were lost in just 6 days as the snow began to melt. Turns out 9 pounds of nitrogen per acre of that 100 were lost in just 6 days, and over the next few days, more was lost. So this is a pretty significant economic loss for producers. How about high-risk conditions for nitrogen leaching? So for nitrogen to leach, we need 2 different things. One is we need deep percolation. Deep percolation is defined as water that moves below the root zone. The second thing we need is high levels of nitrate in the soil. We also, generally, nitrogen leaching is going to be higher, of course, in coarser soils where water can move more quickly. Irrigation can make nitrate leaching worse. High rain events when there's no crop in place to take up water, so fallow. Fields with high amounts of residual nitrate and no crop to take it up. Any questions so far? So mainly I've covered the nitrogen cycle. I've covered urea and high-risk conditions for urea volatilization, high-risk conditions for nitrate leaching. And last week, I wanted to thank those of you who provided constructive criticism, as we call it in education. I got 3 major pieces of advice. One was to use a larger pointer. I also chose to use an obnoxious color, so it really stands out. A little more light on my face. And I'm wondering, again, I was asked to leave a little more time for questions. So does harrowing count as tillage? So the real trick is getting the urea down into the soil about 2 inches. Above 2 inches, it still has a good chance of volatilizing. So I would say, depending on your piece of equipment and soil, for the most part, harrowing is just not going to move much urea below 2 inches. So I would say no. Other questions? And again, feel free to ask questions anytime.
Oh,
Go
Clayne,
ahead. Yeah.
did you see that next question?
How is the nitrogen loss from the snow measured in the example? So that's a great question and worth going back to. So my colleague Rick Engel installed 5 to 6 of what he calls shuttles. So these shuttles are on, not sure if you can see this, it depends on your screen size, but they're on these white apparatus that are on a post that can swivel. And so the shuttles always face upwind. Inside the shuttle is a filter with a chemical on it that ammonia attaches to. So about every week, Rick or his technician Rosie had to run up. Generally, this was in Hill County, collect these 5 or 6 shuttles, swap out a clean filter, take the dirty filter back to the lab, and analyze it for ammonia. And then he compared that amount of ammonia on those filters to a control where he had these masks set up somewhere else in a place that did not have urea volatilization. And then with some fancy math, he was able to calculate how much ammonia was lost. So great question. Okay, I'm going to move on, but again, feel free to always ask questions. So now on to rate and to source. So in general, a lot of times I hear people say, I didn't want to leave any yield on the field. So I wanted to really maximize my yield, and therefore I applied a fairly high rate of nitrogen. Now, the problem with that, of course, is if the year is dry, then what you do leave on the field is a lot of nitrogen, but maybe you don't maximize yield. So this is a curve showing the concept of the law of diminishing returns, which shows as applied nitrogen goes up, crop yield in bushels per acre also goes up, and this is from actual data in Montana. And the rate that yield goes up is pretty quick for those first, 100 or so pounds. But above that point, the yield really starts plateauing. And what else goes up? Well, what else goes up is cost of the nitrogen fertilizer. And the other thing that would go up is the amount of nitrogen leaving your field, possibly as leach nitrogen or volatilized nitrogen. If you want more information on these tools where we have the best nitrogen rate shown for spring wheat, winter wheat, and barley following fallow, you can go to this website. So again, the greatest yield increase per pound added is at low rates of nitrogen. At a certain nitrogen level, additional nitrogen doesn't produce any additional yield. And of course, this is for a fairly high yield or yield potential of 80 bushels per acre. So some downsides of higher nitrogen rates. And by higher, I don't mean, increasing nitrogen at low end does increase profit. At high end, it often has additional problems. So here's a graph from some work done in Big Sandy by my colleague Perry Miller and me, where we looked at nitrogen rate in pounds of nitrogen per bushel on the horizontal axis and the 8-year net return, so profit in dollars per acre. We did that for both low protein discounts or flat protein discounts and steep or high protein discounts. And what it shows is, at low rates of nitrogen, the net return is not nearly as good as at kind of moderate rates, somewhere right around 3 pounds of nitrogen per bushel. The profit tends to about maximize, but especially this low protein discount, if we apply more nitrogen, our profit goes down. At these higher protein discounts, it stays about flat or maybe creeps up a little bit. Another downside in that same experiment is we found that as we applied more fertilizer nitrogen, soil pH in the top 3 inches dropped pretty dramatically for just an 8-year study. So acidic soils are becoming a bigger problem in Montana. And on this particular field, you can see that pHs have dropped to about 5.6. Probably in another few years, they'll be 5.2. And below 5.2, we start seeing aluminum toxicity. Below about 5.8, we find that pulse crops don't nodulate as well and they don't fix as much nitrogen. So what I'm showing here is that higher rates of nitrogen result in lower pHs for both a legume grain winter wheat rotation and for a fallow winter wheat rotation. It does appear that if we don't apply too much nitrogen to that legume grain wheat system, we do end up with higher pHs than in the fallow system. Moving on to nitrogen source. So nitrogen sources have different volatilization and leaching loss potential. So there's a whole bunch of nitrogen sources available to producers. Urea is the most common, but there's other ones like ammonium nitrate, hard to find, calcium ammonium nitrate, expensive, ammonium sulfate, which is used with seed as a sulfur source. All three of those have relatively low potential loss for volatilization compared to urea, as does UAN, but all of them have similar leaching potential losses. There's also products called enhanced efficiency fertilizers. These include things like the urease inhibitors, agrotane being the most common, nitrification inhibitors, combinations, controlled release, and slow release. Some of these have less potential for volatilization. Probably the most studied are these urease inhibitors, almost always show less volatilization loss than urea. Some of these combination products also, these slow release products as well. Many of these products have less chance for leaching than conventional products. Some we just don't have enough data to know for sure, especially in our region. So what about looking at some actual data? This work was done in Oregon, where the researcher Don Hornak applied nitrogen as 4 different sources on a newly seeded grass field, and he monitored nitrogen loss as ammonia in percent. What he found was that, kind of similar to what my colleague here, Rick Engel, has found, he found urea had losses upwards of 25%. UAN was about half of that. So urea ammonium nitrate is half urea. The other half really doesn't volatilize the ammonium nitrate. Calcium ammonium nitrate volatilizes even less. And then agrotane, at least in his study, volatilized the least. Here in Montana at Coffee Creek, my colleague Rick Engel measured grain protein for 2 different products, urea and also urea with this product called NBPT, which is a urease inhibitor. So what does a urease inhibitor do? So what it does is it slows the conversion of urea over to ammonium. By slowing that, it turns out that pH doesn't go up as much and volatilization doesn't go up as much. So we also did this over 3 years at 3 different timings, fall, winter, and spring. And what you can see in almost every case, so the gray bars are urea, the blue bars are urea with this NBPT product. Essentially in every case, protein was about 1 point higher with the NBPT product than the urea. So that's pretty notable. The other thing you may be noticing too is that spring applications actually were in general produced a lot higher grain protein than fall or winter. We think there's less tie-up by microbes by applying in spring, maybe a little less leaching loss. So for the most part, what Rick found was that NBPT significantly increased protein. It also increased yield in the fall when applied in 2012. That's not shown here. I'm not showing yield. And also spring timing seemed to increase protein more than fall or winter timing. This is a graph showing yield differences by using a polymer-coated urea, a product that Nutrien makes called ESN for environmentally smart nitrogen. This is on corn. I know corn's, not a huge crop in Montana, but it certainly has increased in the last decade or so. What my colleague Alan Blaylock is showing is the yield difference by using polymer-coated urea in bushels per acre. He did a huge number of comparisons. So what a data point on this side of the curve shows is that by using the polymer-coated urea, there was actually a loss, a yield loss compared to urea. So not so good if you've spent a little extra money on ESN, but on the plus side, anything on this side is a positive, meaning that ESN, this polymer-coated urea, actually produced higher corn yields than using conventional urea. So what I like about this is it shows that there's consequences of using a different nitrogen source, some of them negative. For the most part in this study, they were positive. And some of these yield gains were dramatic, 16, 20, 24 bushels per acre. So the products, yeah.
There was the one quick question about the graph in the previous slide, asking if that graph was for spring grains or for corn as well, with the 100 pounds to 200 pounds of nitrogen applied.
So this graph was all for corn. I'm trying to figure out where the 100 to 200 pounds of N per acre graph was. So the corn, in this study, they didn't say how much nitrogen was applied. Maybe I'm missing the question here. This graph, is this graph for spring grains or for corn as well? Just corn yields. With the 100 pounds of 200 pounds of N applied. They didn't say how much was applied. It was one of the first graphs. Somebody's helping out with the yellow line. Oh, okay. So yeah, so it was here. And this was, sorry, this was for, I'm pretty sure this was for spring wheat. And so yeah, here's the yellow line, and that was for units of nitrogen. So it took 200 pounds, 200 units of nitrogen to grow 80 bushels. We can do the math, divide 80 into 200. We find that's about 2.5 pounds of N per bushel. MSU recommends 2.6 pounds of N per bushel. So pretty close to what we're recommending. So this was for wheat. I hope that answers the question. So a little bit on these slow and controlled release products. The photo here is courtesy of Agrium, which has since been bought up and now is called Nutrien. Slow and controlled release products work by having this thin polymer put around the urea, and then that urea dissolves and slowly basically diffuses out of that plastic polymer. I would recommend a product like this in areas that have high risk of leaching or high denitrification. That doesn't include really, all that much of Montana. And so where losses could be high, these products could really pay for themselves. Where risk of loss is low, probably not. Another risk is applying them too late. So because they take time to dissolve or time to be released, it can be risky to apply nitrogen too late in the year and then not be available when your crop really needs it. One advantage might be, let's say your winter wheat grower is putting down a fairly high amount of it with, say, the seed. Then you don't have to come back in the spring and top dress. And spring, I know, is when a lot of you are super busy. Some of these products might benefit protein more than yield and could protect water quality. Nitrification inhibitors are products that delay the conversion of ammonium over to nitrate. So the reason this could be beneficial is, remember, nitrate can leach. Nitrate can also get converted to nitrogen gas and escape to the atmosphere. So it's possible that these products could be beneficial in coarse soils where there's a high risk of leaching, or in fine soils where there's a high risk of this process called denitrification that occurs more in waterlogged, clay soils. Because neither leaching nor denitrification occurs a lot in dry in dry soils, maybe not in well-drained soils for denitrification, the benefits are probably going to be less. There is one study that showed one of these products, DCD, sprayed before a fall plowdown, can slow nitrification and also leaching loss. Work done in the inland Pacific Northwest on an irrigated field with one of these products, Instinct 2, which is a nitrification inhibitor. Here, the researchers looked at a 0N control, a liquid UAN, so probably 28 solution or 32 solution, and then that liquid applied with two different rates of this nitrification inhibitor called Instinct. What it shows is these different letters indicate that there was actually a significant yield increase, somewhere around, it looks like maybe 6 or 7 or 8 bushels per acre by using Instinct. And that's probably, again, because in an irrigated situation, there's a better chance for leaching and a better chance for losses from denitrification. So this is probably a winner. What about in a dryland system? So same study, but dryland. Here, the urea plus the Instinct did no better. Statistically the same. And again, that's probably because in a dryland system, there was less potential for loss. So might be beneficial for those of you who irrigate, maybe not so beneficial for those of you who don't. Any questions whatsoever on anything I've covered so far with respect to nitrogen?
There was one follow-up question going back to that chart on slide 13.
Okay.
Just the question was if that will follow corn as well.
So that was the same one. Is this slide 13?
Yes.
Okay. So corn needs about 1 to 1.2 pounds of nitrogen per bushel, but it should have kind of a similar shape. The yield will possibly max higher. A lot of corn is irrigated, but this is more showing the general concept of the law of diminishing returns, where we get a big bang for our buck at low nitrogen, less of a bang at medium nitrogen, and then yields plateau. And sometimes in our dry environment, they actually start falling down. So I have not modeled corn yield in Montana just because there's not a lot of data for it, but the general concept would be the same. It just takes less nitrogen to grow a bushel of corn than a bushel of wheat. Did that answer the question, do you think, Jennifer?
Yes, I believe so.
Okay. Other questions?
I'm not seeing any right now.
CCA wrote me and said, I've had seedling burn with high rates of ESN. Problem may be the coating may have been broken from mishandling. And so, yeah, that is something interesting about these polymer coatings. There's been studies showing how they're handled affects the release. And so, if they're on a conveyor belt versus getting loaded and unloaded into trucks, that can slowly wear off that polymer coating till they become like urea. And so you end up kind of with this mixed product of some with coatings and some without. So that you do have to treat ESN maybe carefully because of that coating. Is there similar information that's applicable to alfalfa and hay crops not modeled in Montana? But typically we need, yeah, somewhere around 25 pounds of nitrogen to grow a ton of grass. And we have fertilizer guidelines that I'll discuss later today and in our forage talk, as Catherine mentioned. Does the polymer coating decompose over time? So it does. So polymer is, a nice fancy name really for plastic. And so it's a thin layer of plastic. Some of you have probably heard about microplastics in our environment, but this one at least is, my understanding, is biologically decomposed better than a lot of our plastics. So sometimes you can see them up to a few months after application, and then they seem to be primarily gone, so they will decompose. Good question. Do you know which polymer it is? I don't, and don't even know if Nutrien would provide that information or not. Okay, moving on to nitrogen placement. So in general, subsurface placement or incorporation of nitrogen fertilizer decreases losses and primarily urea volatilization losses because you get that nitrogen below the surface stuck onto the soil where it has less of a chance of escaping back to the atmosphere. Does the application on snow or frozen ground protect from volatilization? Just kind of a review, the answer would be no. As the CCA just mentioned, we need to be cautious with seed place. So germination can be dramatically decreased if a seed is in direct contact with a salt, and fertilizer are salts. So how much water, either irrigation or rainfall, does it take to protect urea from volatilization? Work done again on the west side of the mountains, showing the effects of irrigation rate on the percent of applied nitrogen lost to volatilization. So what it shows, at least in this study, is very high loss rates when no irrigation was applied. But by 0.2 of an inch, the rates had dropped to 20%, 0.4 about 10%. We kind of arbitrarily say, well, a half an inch looks pretty good. Maybe we're only losing 5%. So a half inch of irrigation water, half inch of rainfall should essentially stop volatilization. Something else that you can do is either, like I mentioned, apply a urease inhibitor or put your nitrogen deep enough where it won't volatilize. So this was a study done on canola where nitrogen was either broadcast, placed 1/4 to 1.5 inches deep, and this is after packing, or 2 to 4 inches deep. What it shows is that broadcast products, there was a major disadvantage of using urea and a major advantage of using these two products that have a urease inhibitor in them. So there, the urea sat on the surface and volatilized. The other products slowed the amount of volatilization. When that nitrogen was put 1/4 inch to 1.5 inches down, the benefit of these urease inhibitors was somewhat less, but really it didn't equal out until the nitrogen was placed 2 to 4 inches deep. So what that tells me is below 2 inches deep, urea must not volatilize because it did no worse or no better than the NBPT or the Super U product, which also has NBPT in it. So kind of gives you two options as producers. One would be use a protected product if you don't want to lose 4 or 5 bushels per acre of yield, or bury your nitrogen subsurface, band it at least 2 inches deep. And then it doesn't matter what product you use, you might as well use urea because it's less costly. Timing application of nitrogen is also important, and timing discussed by itself isn't as relevant as discussing it with the product, because the product really matters. So these readily available products, you probably want to get in the ground sometime, shortly before seeding up to maybe mid tillering. And I have more information here on how nutrients take up nutrients, how quickly they take up nutrients, depending on the crop. Slowly available nutrients like manure and slow release nitrogen take time to become available. So those really need to get put on the ground a little earlier, maybe as early as late fall or early spring. This is some work done in South Dakota in a fairly similar rainfall environment to Montana, where they looked at 5 different timings and placements of nitrogen. Their control was urea broadcast at seeding, and they conducted this study for a very long time and kept repeating the study. So, almost 17 years. Here on the vertical axis, I plot net revenue difference from urea broadcast at seeding, which is shown here as the black line. So urea broadcast at growth stage Fekes 4, plus some more nitrogen streamed on at joining, did a little better. Urea broadcast at the F4 stage did slightly better. UAN banded at seeding did somewhat better, especially in the later part. And then the best system almost every year was UAN mid-row banded at seeding, and then another nitrogen application called streaming put between the rows at jointing. So that probably best matched the nitrogen needs of the crop and produced the highest profit in each year. Over here, I've also put the yield in bushels per acre, which really wasn't that different between the different systems, but there were different costs, and certainly this one did pretty well. Any questions so far? Okay. Any questions on your end, Jennifer? Maybe that went directly to you?
Nope, I haven't gotten any.
Okay. Okay, so on to crop rotations. So again, one of the things I've mentioned is if we can keep nitrate out of groundwater, that keeps your groundwater cleaner, better drinking water, also fewer losses, keeps more nitrogen in your crop. So this is a 6-year study done out of Sidney, Montana, where they looked at groundwater nitrate in parts per million. 10 ppm is the drinking water standard. And what they plotted here was nitrate concentrations over time for 3 different crops: a small grain, sugar beet, and safflower. Notice that the small grain crop had some years where the nitrate concentration, or some times of year, when the nitrate concentration was above the drinking water standard. Sugar beet did a little bit better than the small grain, and then safflower, which is the deepest rooted of the three crops, kept nitrate levels the lowest. So by having a deeper rooted crop, nitrate that's trying to escape to groundwater can get sucked up and not escape to groundwater. So having safflower or another deep rooted crop like, say, alfalfa, most perennial grasses, sunflower, that can really help decrease nitrate leaching. Something else that leaves less nitrate in the soil to leach would be decreasing the amount of fallow. So this work is based on a 37-year study out of Saskatchewan where they monitored nitrate in pounds of nitrogen per acre and plotted that versus soil depth ranging all the way to about 15 feet deep for 3 different crop rotations. Fallow wheat in yellow, this line, fallow followed by wheat, and then another year of wheat in the dashed kind of gray line, and then continuous wheat in the green line. So what it shows is the system that had fallow every other year had, as you might expect, the highest amount of nitrate at depth because simply there wasn't a crop there to take up the nitrate every other year. When fallow only represented 1 in 3 years, the nitrate levels were substantially less. And then continuous wheat had the lowest levels of nitrate, at least at depth. So decreasing fallow should decrease nitrate. A little closer to home, on a study that I worked on called the Judith Basin Nitrogen Project, here we compared, excuse me, we compared a pea that was grown for grain, followed by winter wheat, with a fallow winter wheat rotation in both 2013 and 2014. And we plotted the average estimated nitrate leached in pounds of nitrogen per acre. So in 1 year of the study, 2014, there didn't seem to be a big difference between them. But in the first year of the study, the amount of nitrate leached in the fallow winter wheat system was 50 pounds of nitrogen per acre. That's a pretty big chunk out of maybe 80 pounds applied compared to only 18 that was lost in that pea grain winter wheat system. So again, both in Saskatchewan and here in Montana, decreasing fallow should decrease leaching. This was kind of a win-win system because in one of these 2 years, the pea grain followed by winter wheat also produced more profit than fallow winter wheat. In the other year, it was a wash. So what are some nitrogen management factors that you can adopt to decrease nitrogen leaching? One would be applying nitrogen based on a spring soil test, using a conservative nitrogen rate at seeding, and then applying a second application, say maybe as a foliar or streamed on, only if it's a wet year. Avoiding fall application on shallow and or coarse soils, and consider applying less nitrogen in areas that yield less or maybe have shallow soil. So doing some sort of variable rate application, as my colleague Jerry Nielsen used to say, farm soils, not fields. And recrop when possible or grow deep-rooted crops and perennials. Any questions on anything that I've covered so far? Okay, so things that some of which might be intuitive, others less so. Microbial activity will be higher when moisture and temperatures are high. Here we have some work from memory done out of Canada, where we've plotted the amount of plant available nitrogen from urea, where plant available nitrogen increases very quickly. Immature alfalfa cover crop, where it increases more slowly. And then also from a mature alfalfa hay crop where there's not a lot of release in the first few weeks, probably because those big old tap roots don't break down very quickly, but the release of nitrogen continues to occur for many years after a mature alfalfa hay crop. And this yellow one here is after a pea that is harvested for grain, it's residue. So it really doesn't release much nitrogen immediately, but again, in the long run, it can release quite a bit of plant available nitrogen. How much nitrogen is lost in straw removal for livestock use? So kind of thinking about maybe a mass balanced weight. There's roughly on order about 20. Oh, in straw. So straw has like an 80-to-1 carbon to nitrogen ratio. It will have a ratio somewhere around 160-to-1 of pounds per pound of nitrogen. So not all that much. Kind of doing the math in my head here, which is always risky. I would say it's around 14 pounds of nitrogen per ton. And so you are losing some nitrogen with your straw when you're using that either, probably most likely as bedding. Straw also has a fair amount of potassium, and I have run some numbers where I sometimes question whether the nutrients lost by removing your straw really pays for the benefit you're getting from that straw. It probably depends whether you're selling that or whether you're a livestock producer and you're using it. But certainly you're losing some nitrogen with that. So plant available nitrogen will depend on how leafy or green that material is. Mature plant residue generally has lower nitrogen concentration. The nitrogen amount for the next crop, how much you can back off your nitrogen fertilizer for the next crop, is called a nitrogen credit, which I'll discuss next week. Jumping back to economics and thinking about what rotations are more profitable. This is again that study done in Big Sandy where we had chem fallow, a cover crop that was harvested as hay, a legume grain crop, and then a continuous wheat crop. We calculated the 8-year net return or profit in dollars per acre for those 4 different systems for both a high protein discount, a low protein discount, or flat protein discount, or a steep or high protein discount. And what you can see is regardless of protein discount, the most profitable was a legume grown for grain. This was lentil 1 year, pea another, and chickpea in a 3rd year, followed by wheat, whereas continuous wheat, the cover crop, and chem fallow wheat all did noticeably worse. So just to sum up, a combination of management changes is likely needed to substantially increase nitrogen use efficiency. I would recommend managing nitrogen with the end cycle in mind to supply the nitrogen when it's needed, where it's needed, to reduce losses and protect soil, water, and air quality, as well as your pocketbook. Of course, each growing season and each region in Montana is going to have unique best management practices to increase nitrogen use efficiency. And research can't test all possible conditions. I can give you a guideline for Montana, but Montana is a really big state. So I really recommend if you want to try out a new product, do strip trials. Run a product in 1 or 2 strips on your field, flag it, maybe GPS it, and see if it does any better. And that will be the most useful for your field rather than me telling you what to use or what not to use. So thank you. And are there any questions from anything I covered today? I do want to point out that this presentation and more information on soil fertility will be here. And again, in probably a week or 2, I'll have the transcript and a link to a YouTube video of today's presentation. Questions? Thank you for the thumbs up. And as you can see there, my extension associate, Catherine, just added a link to a survey that will help us with these presentations, especially if you weren't here last week and this is your first week, and anything you can suggest to make these presentations more relevant and useful to you, we'd appreciate it. They're anonymous. All right, well, I'm going to stop the recording unless there are any last minute questions. You can always unmute if you'd rather ask the question verbally than in the chat.
Yeah, I just wanted to thank you, Clayne, just for being able to put these webinars together. It seems like we're continuously learning, but best practices and better ways to get information out to everybody. So these have been really awesome, and I'm sure the remaining portions of the webinar are going to be good too.
Well, thank you very much, Jennifer, and I really appreciate you being willing to host today.